Okay, do you mind if I record the talk?
It's okay for me.
That's perfect. So I think you are in a position to be to put your slides if you like.
Yes. I think I can share my screen now.
So you are extremely welcome. Sorry, there was this question, this technical question. I will. Okay, I don't know how.
Technical issues are overwhelming. Moreover, in this pandemic time.
Yes, it's complicated. Yes, I'm sorry. Okay, so I will try to work out the question on the computer. It will be more nice, but please go ahead.
Okay. First of all, Paul, let me say thank you for this invitation. So let's start. I am going to tell you today some words about this topic, stochastic persistence in the context of ecological communities, okay? And more specifically in the context of stochastic ecological communities driven by Levy noise. So this is the topic of this talk. Okay, so
L'université de Valparaiso.
I'm sorry, I really need. Je peux passer dès que je peux.
L'université de Valparaiso.
Excuse me.
Sorry, who is speaking?
Gilles Durier.
Sorry, I don't know.
Yes, it seems that Gilles was speaking. But...
Someone is speaking, but I don't know who. Sorry, because
okay.
I don't think it's me. And wait,
let's continue. Okay, so let me start with some with a very easy example. Maybe far too easy for all of you, but nevertheless, it seems important to me to try to explain the things from the beginning. So let's start with a simple Lotka-Volterra, stochastic Lotka-Volterra prey-predator model. So here we have two stochastic equation, okay, a stochastic differential equation. The first species, the abundance of the first species have the superscript 1. The abundance of the second species have the superscript 2. And these are the equation. Here is here we have two independent Brownian motion. Okay, here is this is a very simple model of interaction between two species.
Oh,
the first one is considered as a prey, okay, so it has a positive growth rate, and the second one is considered as a predator. So the predator can only grow in the presence of the prey. So if you have no prey, the predator dies, of course, okay, but the prey, say the plant, okay, can live, can persist, but I haven't told you what is persistent yet, but intuitively it can persist even in the absence of predator. So this is a very simple model, okay, of prey-predator dynamics. Let me introduce some notation here. You start with initial condition on the positive orthant, on the positive cone, okay, and this is the notation for the positive cone, Rm plus, okay, and Rm plus plus is the strictly positive cone, so where all the entries of the vector are strictly positive, okay. Let me introduce also the simple notation. Here we have a flow of biomass from 1 to 2, so from species or taxa with index 1 to species or taxa with index 2. So, okay. So let me say some words about the biological interpretation of the coefficient that are present in the equation. So the BIs are the per capita per unit time birth or death rate. So if we put a minus sign before the BI, so this is interpreted as a death rate, okay? Aij, okay, for I not equal to j, okay, are the interaction strength. So in our case, we are going to consider just interaction of feeding interaction. So I is eaten by j, or the other direction, That is in the case if I is not equal j.
I'm sorry. We repaired the thing. I'm sorry. Now it's fine. I'm sorry if you don't mind. I prefer if you would you come back, because we didn't see at all your presentation from the beginning.
Okay, so I mean this coefficient. This coefficient here, Aij, okay? So when I is different from j, for example here, so this is the interaction between species, okay? Okay, and this interaction is going to be considered just as a feeding interaction. So I is eaten by j, okay, or the other direction, or the other way, okay? And when I equals j, okay, so this is considered as an interspecific competition, okay, maybe due to competition for space or light, etc. Okay, here the sigma i's here are just the amount of perturbation, okay, due to environmental noise. I'm going to say some word about this idea of environmental noise. Then, as I have said, W is a standard, in this case, a standard 2D binary process, okay, carrying the environmental noise. So, some word about this idea. So, the stochastic, it's very important from the modeling point of view, okay. It is assumed that the stochastic perturbation of the fitting, because here you have, this is the rate at which here I miss a dt, okay. Of course, here I miss a dt, if you can see that. Okay, here is the deterministic part, okay, the deterministic rate of change of the fitting, okay, of the species I, 1 and 2, okay. So here is a stochastic perturbation at the level of the fitting, okay. Okay, and it's important to say that we must keep in mind that the perturbation of the fitting, okay, have a characteristic time, okay, much shorter than the time horizon that is relevant to our observation, okay. Well, okay. That is a very simple model, of course. I'm going to consider more complex model than that, okay. But indeed, in this work, I'm going to consider communities with n population, okay, indexed by a finite set, okay, engage in a log-cabal terra dynamics, okay, driven by continuous and jump time noise. And what's the problem I'm going to address here? So we ask what are the conditions at the level of the parameters of the equations, okay, that allow us to say that allow us to ensure that the whole set of species persist, okay. But again, I haven't defined what is persistence, okay. First of all, let me say something that maybe it's a simple exercise, okay. It can be proved that if you start from initial condition on the strictly positive order with a strict positive condition, so there is no absorption in finite time, almost surely. So if you start positive, you always remain positive, okay. This is the first thing. So any any idea about extinction, okay, is an asymptotic, is a claim, say, is a claim about the asymptotic law, okay, the asymptotic behavior of the law, okay, of the law of the process, okay. So here's a first version of persistence, okay, in the context of ecological communities. So we say that a certain subset, okay, of the entire community stochastically persists in probability if with high probability you have that for long times the subset of abundance indexed by J, okay, remains in a compact set far away from extinction. So far away, observe this means that we are far away from extinctions because we are this is a compact set of the strict positive cone, okay, and it's compact, of course, so you don't have abundance, too large abundance, okay. This is the first approach to a concrete definition of persistent, okay. Then you can have other definition. For example, you can try to weaken a bit this definition. For example, by something like stochastic persistent in average. So there is a lot of definition of the kind, okay. And indeed, there is some work, previous work from Bao, Mao, Jin, etc. So the Chinese school, say, that have dealt with this kind of persistence in the context of indeed levy-driven Lotka-Volterra system. So, okay, what we are going to deal with a stronger version of the notion of persistence. So observe that again in a system like the first example. So this is a running example for just for didactical sake. Okay, observe that here we have if this is not zero, so we have a quadratic drift to the origin. So and here also. So we can expect to have some good reason to expect to have invariant law, so non-trivial invariant law. Okay, and this fact, if we add the unidirectional sense of the energy flow, so there is a very well-defined sense of the energy. So we well from 1 to 2. So we have no cycles. Okay, these two conditions give some warrant that there are invariant laws. So the notion we are going to deal with is a claim about invariant laws. Okay, so, and then we ask, when you start from the strict positive cone, okay, we ask two questions. When do the law of X, of the process X, okay, converge in, for example, weak sense or in the total variation sense, okay, to a unique invariant probability measure pi, okay? So if you start from the positive abundance, we want to know under which are the conditions that guarantees that we converge to a unique, okay, invariant probability measure pi, okay. And then we want to ask what is the nature of this invariant measure, because okay, I have said that in finite time you have almost surely no extinction, but that is for finite time, okay. So in principle it is possible that even if you start from positive abundance, asymptotically speaking, the law charts the boundaries of the positive cone. Okay, so we want to know if the invariant law, okay, supports, okay, the whole community or just a strict subset of the community. Okay, and this is the definition. So the intuitive definition: if this unique invariant law, okay, to which we converge from when it started from every initial condition, the positive order, if this invariant law does not charge the boundary, okay, of the positive cone, so if under pi all the species are alive, all the species are have positive abundance, then we say that the community is a strongly stochastic persistent. Okay, and here is the formal definition. We say in general, okay, not just when we refer to a population model, we say that our Rn++ valued right continuous Markov process, blah blah blah, okay, is SSP, okay, if we have a unique invariant probability measure supported or Rn++, okay, so this means this here, this physiology, okay, means that pi, let me use other color maybe, pi of the boundary, okay, of the positive order equals 0. So it put no mass, okay, on the boundary, okay, and such that for every initial condition you have convergence in total variation distance. Okay. Okay, this is a definition given, for example, by Henning and Dan Nguyen. Okay, but you can find it also in the recent paper from Benaim, from Schreiber. Okay, Benaim. Okay, Schreiber. So there is a lot of researchers that are working with notion like this. Okay. Okay. First of all, here I have here I made a mistake. Okay, this is not X. This is of course P erg. Okay, this is the set of ergodic measure. Okay. For the process X, okay, and let me okay, this is the set of ergodic measure of the process, okay, associated to the semigroup, the process. So, of course, the set of ergodic probability measure, okay, is not empty because the point where we have no abundance at all, so all the species are extinct, is trivially ergodic. So, well, but then you have a lot of, in general, a lot of invariant measures. So again, if we refer to the first example, okay, you see, for example, that this set, okay, so the set where these first the species indexed by J, okay, are alive, but those in the complement are dead, okay. These are invariant set for the dynamics, okay. And so we can expect to have a lot of invariant measure, okay, on Rn on the whole cone, okay, say on the closed cone, okay, and many of these invariant measure is it possible that they are concentrated on the boundaries, okay, and remember that the boundary is the set where at least one of the species is extinct. Okay, so okay. These are the ingredients, okay. And then we have to make a. Oh, okay. There is this crucial insight that I want to explain here in a rather intuitive way. So, okay, suppose that you have invariant measures supported on the boundaries, okay, and indeed you have, because if you kill one species, okay, and let the other evolve, okay, under certain condition, you can ensure that you have a invariant measure for this subcommunity, okay. So pick an invariant measure where at least one of the species is extinct, okay, and call this measure, this probability measure mu. So okay, so mu put positive mass, strict positive mass on the on the boundary, okay. And then suppose that the process X, when started from a strict positive abundance, get close to the part of the boundary that is shared by mu. So assume that for long time, for large time, okay, you start from positive abundance and you get closer to the part of the boundary that is shared by mu, okay. So in that case, we can say that in order to avoid that measure, okay, we need that under mu, okay, the endangered species, so the species that are going extinct, okay, that are reaching the boundary, okay, they need to grow rapidly, okay, in order to avoid the extinction fate, okay. Okay, this is the crucial idea. So if we assume some regularities, okay, on the property of the semigroup, okay, etc., we will see that this will amount to ask that under invariant any invariant probability measure that shares the boundary, okay, at least one of the species absent species has a positive Lyapunov exponent. So the idea here comes from the theory of differential dynamical system. So indeed, this has been borrowed, I dare to say, from the theory developed during the 80s and 90s in the context of deterministic dynamical system by Hofbauer and collaborators. So this is the crucial insight I dare to say. So okay, so let's come back to our example. So to the first example. So here we have a community. This is the prey, okay, the plant, and this is the rabbit, okay, the rabbit, okay. Okay, and so you have the entries of the matrix. Okay, here we have that A21, okay. This is greater than 0. A12, this is smaller than 0, and you have interspecific competition here. Okay. So okay, we ask, how do we ensure a strong stochastic persistence, this property, okay, for this very simple system? And so let's follow the insight, okay. We have more than one invariant, indeed ergodic measure, probability measure for this system. The first one, as I have just said, is of course the delta on the origin, okay. This is the point mass on the origin, okay. So we have no abundance at all, okay. And then of course we have an ergodic measure of observability. Maybe a mic is open.
No, porque todavía, todavía está
I think that a mic is open.
No, that's sorry. That's someone
Okay.
entered and disturbed you. Sorry.
Okay. Okay. Observe that in the context of the first example. Let me get back there. Here, there is also an ergodic probability measure that supports the first species and under which the second species is extinct. So if you put positive abundance here and zero abundance here, you have a system that is a one-dimensional system, okay? And this, of course, amount to a particular case of the logistic equation, stochastic equation, okay? And thus, and it's very well known that in that case you have an invariant probability measure, okay, which has indeed the law of a gamma distributed random variable, okay. So this is what I have just said. So you have another measure, probability measure mu, okay, under which the species 1 persists, okay, and species 2 is extinct. Thus is concentrated on this set, okay. This is invariant, of course, for the dynamics, okay, and it can be shown that this probability measure is unique, okay, and correspond to the tensor product of the measure m, okay, and the delta on zero. So you have zero abundance for the second species, and m is the law of a gamma distributed random variable. So this is a very well-known result, okay. So okay, you have two probability measures about which you have to worry about. This probability measure put zero mass on the put positive mass on the boundary of the cone, okay, of the orphan. So now apply formally, okay. Of course, this is just formal because we have to well, in this case the formal is just right, but in general we have to consider the case where it is possible that this martingale here do not exist properly. So apply formally the function, okay, the eta formula to this function, okay, to the function to each vector x, okay, on R2, okay, apply log x1 and log x2 respectively, okay, and divide by t, and you get this formula here, okay. And here you have, of course, two local martingale that indeed in this case are actual good martingales, okay, and define this object here, okay, this object here and this one here, okay. So you see this is the finite variation part, okay, of the semi-martingale decomposition, okay, of the function log x1 and log x2, okay. So this is important to retain because this is going to be a general fact, okay. So this C1 and C2, okay, are these quantities here. So this depend only on the coefficient and the x, okay, the coefficient of the equation. So what's the idea here? If you let run the time, okay, if you start with from positive abundance, okay? If if for a long time you get close to, for example, a part of a part of the ortan, of the boundary of the ortan that is shared by mu, so morally, this here, this part here, okay, this here and this here, okay, are more or less, okay, mu C1 and here mu C2, okay, because this is an ergodic average. So and if mu is ergodic measure, so morally you have that this for a long time, if you are close to the part of mu that is shared, okay, with positive probability, so morally you have that for a long time, this must be close to this quantity here and this quantity here respectively, okay. Okay, if x spend a lot of time close to the support of mu, okay, this is the first insight. So okay, and then the second one is that for the species that under which the species that under mu has positive abundance, okay. So, for example, in our case, the first one, okay, okay, you need to have that these integrals, okay, are zero, okay, because observe what does it say? It says that this is morally an Lyapunov exponent, okay. So because these are zero mean martingales, okay. Okay, so if you have an stable community, so an stable subcommunity, so the abundance that correspond to that subcommunity cannot grow exponentially fast and cannot go extinct exponentially fast. So in mean, you need to have a zero Lyapunov exponent, okay, for the stable community, okay, the resident species. So those that are supported by mu. So if the species I is supported by mu, so you need to have this, and this is a theorem, and this is proved indeed, okay. But then the requirement that when rare the species need to grow rapidly are translated into this condition here. So the first one is that when you integrate the first one of two, the first one of the second Lyapunov exponent, so against the delta zero, the measure that puts zero mass on both abundance, you need to that this quantity be positive, okay, and then you need that when the second species, the predatory species, is rare, okay, you need that. Remember, mu here in our example here is m times delta zero, okay. This is the law of a gamma distributed random variable, okay. So when the second species is rare, okay, this is the translation of this idea, okay, the predator tend to grow exponentially fast, okay. So in mean it has a positive Lyapunov exponent, okay. So if you can solve the equation, and the first equation amounts to ask this, okay, and the second equation amount to ask this. Here I have written this way to here is zeta. Z is a random variable distributed as m, okay, where m, remember, is the law of a certain gamma distributed random variable, okay. Then here we can indeed have the expression of the expectation of that gamma distributed random variable. And then we can replace in the first equation and obtain this one. This is the condition for a strong persistence, okay, a strong stochastic persistence in the case of this simple community, okay? This is just an example, and but all the ingredients are here, okay? Then, okay, what have I done? I tried to extend, okay, this result to communities, okay, that are complex communities, say, so you can have a lot of traffic levels, okay, and more importantly, the driving noise is Levy noise, okay. A lot has been done in the context of Lotka-Volterra or even Kolmogorov system driven by continuous martingales, okay. But there, as far as I know, there is no work, okay, in the context of a strong stochastic persistence, okay, for a system driven by Levy noise, okay. Maybe I'm wrong, but I think that that's the case. Okay, so here is the general system we are going to deal with. So again, here B is a vector, okay, is a vector on Rn, okay. This is a matrix A, okay, a matrix on Rn times Rn, okay. Here, this is also a matrix that, for the sake of simplicity, there is no harm if we consider this as diagonal for the moment, okay. And this is a good function, okay. This is a function L from Rn times Rn into Rn, okay. Here we have a compensated Poisson random measure, okay. Here again we have the Brownian motion, okay. And this is the Adamar product, of course, okay. Okay, this is the general form of the equation we are going to deal with, okay. The compensated Poisson random measure, okay, has intensity measure given by this one, okay. Here, nu dz is a Levy measure on Rn, okay. In general, but then we are going to impose a very some constraint because in general it's not possible. I haven't been able to establish a condition for every Levy measure. Okay, so under certain situation, I have been able to establish a condition for a strong stochastic persistence, but we have to impose some constraint on the Levy measure, of course. Okay, so from the biological point of view, okay, what does the Levy noise means in this general case? So remember that what I have told you before at the beginning, the Brownian part, okay, is intended to model a rapid, fast perturbation at the level of the environment, for example, luminic perturbation or temperature perturbation. And then in this, if you have that interpretation in mind, so the jump part must is aimed to model a perturbation of whose times, okay, whose time scale, okay, are much longer than those of the perturbation model by the Brownian part, okay. So, for example, you can have a perturbation due to a resident, so a species incoming from the boundaries, okay, of the focal ecosystem, okay, or a massive weather perturbation, etc. Okay. Okay. Observe that the sign of A, okay, of the matrix A, determine a directed graph. So here I have to put also some restriction on the type of community that our framework is going to deal with. Paul, I think I am running short of time. This must end when?
Oh, sorry, yes, but what I mean is that due to the technical issue, I think if you have some, you can take some more minutes.
Yes, yes, yes. Let me finish. Yeah, let me finish with trying to state the main theorem and the assumption. So, in order to complete that part, unfortunately, I'm not going to. It will not be possible to give the example I wanted, but okay. So the communities we are going to deal with are communities that have a very well-defined sense of flow of energy. So, for example, I have I don't treat situation like this. So when you have, for example, autocatalytic communities, okay. Okay, this is a first condition, okay. But then you have some condition at the level of the Levy measure, of course, and the condition on the L function. This can be considered as a response function, okay. So if the environment is perturbed by Z, okay, then the species are perturbed by L, okay, when we have abundance on X. Okay, so the first condition is square integrability of the Levy measure, and this left out a lot of possible Levy measure first. Okay, but it's impossible to work without this minimal integrability condition. Okay, so the second condition is that okay, the response is similar. Okay, at least it's not greater. The response of the species E is not greater than the response that the perturbation on the I component, okay, of the noise, okay, of the jump, say, okay. Then we have this condition that, okay, this is a strong condition, okay. They say that no matter how big X can be, you always have this bounded in this way, okay. And this imposes a strong control, okay, on the jumps of the associated to the jump part, okay. And then we have, of course, a certain locally Lipschitz condition that is important in order to get good property at the level of the semigroup, in particular the Feller property, okay, that is needed to guarantee a lot of technical stuff, okay. Then, okay, just like in the example of two communities, we define the invisibility rate that are going to be integrated against the measure. Remember, they are going to be integrated against the measure supported on the boundary. So these guys here are called invisibility rates, okay, or invasion rates, okay. Then observe that in a layered community. So what have I said? A layered community is a community like this. So you have interspecific competition, okay, and a well-defined sense of the flow, okay, with no autocatalytic cycles, okay. Observe that in a situation like this, you can always find a constant, okay, CIs, okay, for every taxa I, okay, such that if you have something like I fits J, okay, so Ci Aij is greater than Cj Aj. You can always have, you can always find constant that do such trick, and this is important in order to get Lyapunov Lyapunov function, okay, that guarantee a strong drift to the origin, okay. Well, this is an important observation, okay, in order to establish the assumption. And the other one is that the condition that for every ergodic measure supported on the boundary, you have at least one species that has a positive Lyapunov average Lyapunov exponent, okay. This property here can be proved to be equivalent to this one here. So here you have a, so this you can say that this is like a weighted sum, okay, of the invisibility rate, okay, has is positive for every when you integrate this weighted sum for every probability measure, ergodic probability measure supported on the boundary, okay. This is a result from Schreiber, Benaim, and Achade, okay, and is a consequence of the minimax theorem, okay. Well, and the other assumption is that condition 3 holds. So this is the condition that holds. As I have just said, this is equivalent to ask this one, okay. These PIs are positive, strictly positive, and are going, and of course they can be fixed, okay. So if you find a set of PIs, okay, that do this trick, okay, then you can scale this for any positive constants as large as you can, as small as you can, and you can still have this condition. So this is an important flexibility, okay, that give this this form of the hypothesis there. And okay, finally, when you have PIs, okay, that satisfy the conditions there, okay, of display 3, and with the C's, okay, as I have explained before here, these guys here, okay, then you can define this kind of function, and then for some small positive alpha, okay, small, say less than 1, and indeed very, very small in practice, okay, you can define this tilde W, okay, that is the alpha powered of B hat, okay, hat B, okay. What does this function looks like, okay? For example, in 2 dimensions, okay, this guy is like a bathtub, okay, at least for a very small PIs, okay. If you have that the PIs, their sum is less than 1, okay, you have indeed these 2 conditions. So you have a norm-like function. So for large X, this B hat explode, but also for X where at least one of the coordinates goes to 0, you also have explosion of the B hat, and this is the type of function that you need to control both, okay, non-explosion to infinity, okay, and the idea of not getting too close to the boundary, okay. And this is the reason why we call this function log Lyapunov, because it behaves like a norm of logarithm, okay, Okay, so you have explosion near zero, okay, near extinction, and you have explosion, of course, for large value of x. Okay, and you can fix the parameter again in order the PIs again in order always you can fix it in order to guarantee this. Okay. Okay, the final condition is a very technical one. I think I don't have time to do this, but the idea is that some integral, this here, okay, this integral comes from the application of Levy mesh of excuse me, Ito theorem to the function W, okay, formally, okay, to the function W here. So in order to have good integrability, we need that these guys here exist, and indeed we will need this condition here, okay, that is bounded, that is something like a W tilde, okay, and moreover, as a final condition, we will need that the Levy measure, okay, has exponential moment. So this, observe that this condition supersedes the existence of the square integrability of the Levy measure. But okay, at least for okay, well, this is a stronger condition, but in order to make the presentation clearer, I think it's better to put this at the end. Okay, this is a very strong constraint. Okay, the existence of exponential moment. Okay, but then under that assumption there, that is a lot of assumption. Okay, but some of them are very natural. Okay, we can show that from if assumption from 1 to 6 hold. Okay. Then the Levy-driven Lotka-Volterra system, okay, system as I have shown before, is a Feller-Markov process with the property of being strong stochastic persistence. So I think I have run out of time. So Paul, I need
sorry for all those technical problems, but so I really apologize.
Yes, but yes, but nevertheless, I think
okay.
I have talked a lot because I wanted to present a small example, but it's an application example in the context of food chains. Okay, so in the case when you have communities like this, so we have an extension of a result of Henning and Nguyen. Okay, but okay, if someone is interested in this research, may well, we have Paul is going to put the slides on the site.
Case, all the emails of the participants are in the abstract books, so you can contact each other. Okay.
Yes, of course. So when it's interested, please email me, and I'm going to send you the preprint of this work. Okay, it has been accepted in a journal, in an important journal. So, but there is no problem. I can send you the preprint. Okay.
So thank you. Let me thank you for the talk. And so I don't know if there are questions or comments. Maybe we should simply. I'm sorry, Joel, I cannot hear you, but I don't know.
You hear me now?
Oh yes, I hear you now.
Good.
So hi everyone. So I don't know about Enrique. He's how are you? How are you, Enrique? So are you in position to begin right now, or?
Yes. Just a moment. I'm just.
No. I mean Enrique Cabana, because I think the order was, I don't remember. Am I wrong? The schedule was how? I think the schedule planned was I think first with with Professor Cabana and then with you, Joel, no? I don't remember.
Let me just,
May I share the screen or?
yes,
But
Go
in
on.
this case, you need that Professor. Yes, okay. Sorry. Okay, we will manage finally.
I'm just trying to remember. It doesn't matter from,
Okay.
Well,
So that's really a pleasure to see you again, Enrique, and thank you for agreeing to give a talk in this conference.
well, may I start? I suppose.
Yes, please.
Good day to all. Thank you, Paul. I'm very happy to participate in this meeting, and I warmly thank Professor Paul Ducamp for inviting me to present a model for COVID-19 with data from Uruguay. The first version of the model was initially attempted to assess the national system of emergencies of Uruguay at the beginning of the pandemic. But soon it became a sort of divertimento to spend a long time of confinement. My plan is to start with a brief description of the evolution of the COVID in Uruguay, a country with a population of about 3.5 million inhabitants. And then to recall the SIR model in discrete time random version, and finally introduce some particular versions, including the effect of vaccination. I shall use the Shiny applications RBAC to describe briefly the evolution of the COVID pandemic in Uruguay. In the first page of the application shows 4 graphs in the same diagram, namely the amount of active infections and the amount of infected people that has been infected, immunized people, and diseased people. The 4 graphs describe very different amounts of people, and a control button at the left allows the user to select the maximum of the ordinate scale to see better one or another. The actual selection chooses the scale to prioritize the description of actively infected people. That, by the way, is a fair index of the magnitude of the epidemic, but I have just changed the scale, and now it is prioritized to see the amount of immunized people. The first infections were detected on March 13, 2020, and the days are counted starting that day. We have separated the graphical description in 2 very different periods. By almost all the year 2020, the epidemic was controlled by Tetris, the strategy of test, trace, isolate individual cases. This period is shown in page 2 diagrams. By the end of 2020, an increase of social contacts, mainly due to the proximity of season holidays and the impatience of the population for having been many months with mobility restrictions, produced a fast increase of infections. The government failed to adopt sufficient measures of control. In fact, the government developed an ambitious vaccination plan, but did not accompany it with sufficient measures to restrict mobility. As a consequence, when variants Gamma and P1 entered from Brazil, we got the highest rankings of infections in the world. More than 1% of the population was actively infected by April and May. The graph at the bottom of page 3 shows the progress of vaccination. Started at the end of February. The number of people actively vaccinated is in black. Actively vaccinated means 15 or more days after the second dose. The blue lines represent the immunized people by vaccination. There are two lines. The full one is obtained by adding the programmed delay between doses plus 15 days to the date of the first dose. And the dashed one results of adding 15 days to the date of the second dose. And both lines do not coincide because the deadlines were not being met exactly. Let us turn to the model now. I assume that everybody is familiar with the SIR model for epidemics. The model is usually governed by ordinary differential equations with two parameters, beta for the rate of contagions and gamma for the removal. We use a discrete version of the model that assumes that each person follows a Markov chain with states and probabilities indicated in the diagram. Each susceptible person can be infected with a proportional to the relative frequency of active infections.
I'm sorry, there are some interferences. Yes, sorry, please go on. Hello?
Well, and each person infected, I am some trouble about the figures. Well, the people infected can be removed with probability gamma or stayed until the next day with the complementary probability. The time spent with active infections is geometrically distributed with parameter gamma, and hence the expectation is of the time of permanence is 1 over gamma. The sum of the individual processes assumed independent, that is, the vector with components corresponding to each of the states, the number of people that, excuse me, the number of people in each of these states is also a Markov chain, and the transitions from S to I are binomial with parameters Si and Bi, and from I to R are binomial with parameters I and gamma. A deterministic description is obtained by replacing the random number of individuals that move from one state at day I to another at day I plus 1 by the expected number conditional to the present state of the process at day I. The picture shows over a gray background of 50 random paths, the deterministic path depicted with colored white strokes and the averages of a sample of 10,000 random paths in dashed dotted lines. Both are very similar, so that the deterministic paths seem to be a good approximation to the random path expectation. Our model for COVID appears at page 4 of our back. The classes are susceptible after vaccinated, immunized after vaccinated, infected not vaccinated, infected not vaccinated, I am showing in the picture, infected after vaccinated, recovered, and diseased. The dynamics combine the deterministic transitions described in the vaccination and the random transitions as in the simple model that take in consideration the nature of the new classes. The red lines correspond to the deterministic paths of vaccination, and there is a transition to ephemeral states introduced to reflect the non-random motions that are produced each day. And after that, after vaccination, the random transitions are produced as describes the diagram. In page 4 includes the same quantities of the central graph in page 1, 2, and namely the amounts of active infections, cumulative infections, immunized people, and deceased people. But now these quantities are forecasts based on data available at the first day in the diagram. As in previous pages, the ordinate scale can be chosen conveniently to allow viewing easily the desired curves. The user can choose to show the deterministic paths or a number, let me put the active limit of the scale, the deterministic path, or a number of random paths that can be selected by a control button. The origin of the time axis is yesterday by default. Yesterday means the day of the last entry in the COVID external data that are daily updated and automatically uploaded to the program. A control button allows to choose a certain number of days before also. The length of the diagram is selected by other of the control buttons. In the bottom, this says that the diagram is updated today with the data of yesterday. I can show, for instance, let us diminish the length of the diagram and let us see what happens if this is done 10 days ago. Then we find this situation. These are 8 random paths and almost cover the actual performance of the COVID. This is another example with 8 days of delay. Well, I continue with the presentation. The forecast in previous page were computed by extrapolating the series of estimations of the contagion rate beta. The extrapolations are predictions by an autoregressive model adjusting the past estimation from the available data. It can be expected that a model including additional information related to the future evolution of beta would improve the quality of the prediction. In order to include such information, let us take into account the delay dependence of infections with respect to the number of social contacts maintained by each person in the population. The rate beta is roughly proportional to the average number of social contacts of susceptible people. We don't have measures of such contacts, but Google publishes worldwide mobility reports since February 2020, showing movement trends sorted by geographical areas and classified into several categories of places. We, for the sake of parsimony, instead of looking for the best combination of mobility indexes, we have taken the series MI obtained by subtracting the records of retail and recreation and workplaces from the one of residential mobility. Then we explore the correlation between of contagion beta I, which more precisely between the series of estimation beta I of contagion rate and mobilities. The estimation is made by this formula, where SI bar is the weekly average of the number of people that goes each day from S to I, from susceptible to infected. The contagions due to a contact can occur one day, that occurred one day, are registered some days later due to the time of incubation and the delay until the PCR test of infections are applied and have a positive outcome. For this reason, we explore the correlation between beta I and the delay series Mi-H. It should be expected that the maximum correlation between both series be attained with the delay age of about 10 to 20 days. The figures show the correlation for age between 3 and 25, computed with the data available the first day of each month from January to August 2021. Unfortunately, the lack of regularity in the shapes of the curves do not anticipate a very useful use of the correlation. RBAC gives to the user the option of using or not the mobility record. When the control button use Google Mobility Report is off, the future daily transitions are computed with beta I obtained as predictions of an autoregressive model based on available estimations. If instead the control is on, the mobility records are extrapolated the same way, and then each future value of beta is predicted recursively day by day with the vector autoregressive model of the pair beta and mi minus h. The delay h is a random value that maximizes the correlation between beta I and mi minus h in h, where I has a range not too short, neither too long. The procedure does not substantially improve the results. Sometimes it does, sometimes its results are worse than the ones with the mobility button off. The estimation of the variability of the beta include a larger volatility because it adds the random errors of both autoregressive models. And this provides a better confidence limit for the forecast. But since the limits are wider, it confirms also the impossibility of obtaining trustworthy predictions in a process with such an enormous degree of instability of the COVID pandemic. In this figure, we see the actual path and the predictions in orange with control off and in dark orange with control of mobility on, with the data available the first day of each month from September 2020 to August 2021. Besides the deterministic ones in thicker lines. Here I have added the random paths, and one can see that in general the actual path is compressed between the minimum and the maximum of the random path. In these cases, one can see that in general the button on improves the curve with button off, but this is not necessarily the case for other examples. Well, I go to the last page of the model. Some representatives of the political opposition have accused the government of failing to reduce lethality through more effective isolation measures, and in turn, the government spokespersons have described these accusations of scoundrels. To provide the quantification related to this type of comments, RBAC estimates in page 5 the amount of infections and deaths that would have occurred if the contagion rate had been truncated at the values at times in which the recommendation made by government advisors were ignored. The options are the last days of November 2020, the first days of December 2020, and the last days of February 2021. The page offers two different diagrams. The first one shows the amount of active infections corresponding to the newly assumed contagion rate. For that purpose, the transformation that leads to the estimation of the betas is inverted. The transformation includes averages, so the inversion is not exact. The active infections are obtained by running RBAC with estimated betas, but the accuracy of the inversion is verified by applying it with the estimations unchanged And in this zoom, we can see that the reconstruction in dashed line is very near to the original line of infections. Once this is verified, the vector infections are computed with the truncated rates, and here appear in green, in dotted lines. Finally, the number of deaths is estimated as if the proportion of deaths and active infections were maintained. The figure shows that if the contagion rate has been truncated at the November or the February values, I don't remember which one is this figure, more than half deaths of the actual amount of about 6,000 would have been prevented. The gray full line are the actual deaths, the dotted gray line are the virtual deaths, and the dark green line is the difference, the preventable death. I wish to consider now another model. As soon as the first cases of COVID-19 were detected in Uruguay, the National System of Emergencies appointed a small assessing group to analyze the evolution of the epidemic. The group had access to classified information, including the individual clinical history of each person infected with SARS-CoV-2 detected by the national health authorities. The information available includes the data of infections, first symptoms, hospital confinement, transfer to intensive care unit, discharge from hospital, complete recovery or death, whatever be applicable. This led us to propose a Markov chain model with several states of infections according to the health state of each person as shown in the figure. The notations are similar to the ones in previous. The main difference are that now we have 4 classes of active infections. Active infections undetected, detected but not confining hospital, and in intensive care units. And a couple of star states are put in order to render possible the assignment of arbitrary expected times of transitions from a state to each possible destination. I will not enter in a detailed way in which a chain with one state for each number of days with active infections would permit to adapt the transition probability to model any distribution of probabilities and finite transition times as shown in the figure. The diagram of the chain emphasizes the existence of hidden and observed states. The parameters of transitions between observed states can be easily estimated by maximum likelihood from the available data. Then the remaining parameters can be estimated by selecting the ones that led to the simulated path closest to the actual ones, in least square, for instance. In particular, the probabilities of going from the class of undetected infections either to detection or to the undetected recuperation permit to quantify the underreport. More accurate than the least square estimation is the application of the Viterbi algorithm, but the huge number of states of the chain makes the procedure too demanding computationally. But we have discontinued the use of such detailed models because after receiving a report of our group alerting about the risk of exponential increase of infections due to the high instability of the epidemic, the President of the Republic ordered its dissolution. Just a final comment. The addition of the equivalent hidden state of undetected infections to our back, as shown in the figure, is optionally activated with a button in the control panel, and the parameter eta affecting the probability of non-detection can be selected with a slider. By optimizing the quadratic error of 1 and 2 weeks predictions, the underreported infections are estimated in 55% of the document cases. Well, this is all. I think I have recuperated the time. My hearing devices, both biological and electronic, are not optimal. So if there were questions, I thank you for asking them by the chat. And I thank you very much for your attention.
Thank you very much. Thank you very much, Professor Cabana. So are there comments or questions? No? So I don't know. Maybe if there are no more questions, maybe we just thank again the speaker and skip to the last talk.
Hello.
Thank you. Yes. Okay, so thank you very much for Professor Cabana, and thank you really for the last talk of Professor Cohen. Sorry for the misunderstanding. So yes. So hello. Okay.
You see my screen?
Yes, perfect. Okay.
Can you see my screen, Paul?
This is perfect. Thank you very much.
Thank you. I am very happy to join this conference. I thank Paul Ducan for organizing it and for inviting me. It is a privilege. I thank the other speakers for excellent presentations. I want to talk about COVID-19 in a different way from Professor Cabana, a different approach, as you will see. I will talk about COVID-19 cases and deaths in the United States, Taylor's law of fluctuation scaling, and heavy tails. Three parts to this talk. One, analysis of data on COVID-19. Two, simulation of a very abstract model. And three, some mathematics. As of last Sunday, September 12, there were 225 million reported cases of COVID-19 disease and more than 4.6 million deaths. The United States had more cases, 42 million, and more deaths, almost 700,000, than any other country, unfortunately. The administrative structure of the United States has approximately 56 first-level divisions, which I will call states. That includes states, territories, possessions, and Washington, D.C. These are the primary subdivisions, the first subdivisions. Within each of those subdivisions, there are secondary subdivisions called counties. And there are about 3,100 of these. So if you divide 3,100 by 56, the number of counties per state is about 55, which is roughly equal to the number of states. So I will examine a model that assumes as many states as counties per state. If you have questions during the talk, please unmute yourself and talk, because I want to be clear, and if I'm not clear, I'm wasting your time. So ask me questions freely, please. The New York Times has a public database with the final counts of cumulative cases and cumulative deaths. That means everything up to the end of each day. On the 20th of June, I downloaded the data from the beginning of this pandemic to that date. So there were approximately 1.4 million counts by day and county in the data that I downloaded June 20th. And I organized the data like this. Each column, I don't know, can you see my cursor? Paul, can you see my cursor?
Yes, it is okay.
Okay, thank you. Each column here represents one state, and each element is one county in that state. So there are about 55 or 56 columns, and on average, about 56 rows, 55 or 56. So for the cases, cumulative cases, always cumulative. For the cases on each date, I can calculate, and I did calculate, the average number of cases per county in that state and the variance of the number of counties, the variance of the number of cases in the counties in that state. In a separate table, I did the same thing for deaths. So everything is done twice, once for cases and once for deaths. Here's an example. On June 1st, June 1, 2021, the Virgin Island cumulative cases was 3,465. The average per county was this number, and the variance of cases per county was this number. That's at the low end. In California, on June 1, 2021, there were 3.8 million cases. The mean per county was 65,000, and the variance was 3 times 10 to the 10th. I hope that's clear. This is a plot of cases, and here I have to explain in detail, otherwise this makes no sense. So let's start in the top left corner, April 1, the first day of April in 2020. This is very early in the pandemic. This X in the upper right corner here shows the mean on the horizontal axis and the variance on the vertical axis of the number of cases in one state, possibly California, I'm not sure. The axes are log. So this is the logarithmic scale, and this axis is a logarithmic scale. The other x's are the other states. The coordinates of the axes are the same in all of these plots. And what you see is that the cumulative cases start in the lower left corner and move upward and to the right, upward and to the right, up, and they end up in the upper corner. That's the spread of the pandemic. I fitted a straight line by least squares. That's the yellow line. There is a very good linear relationship here. All of the R squared coefficient of determination exceed 0.9. And the slope of this line is in the top left corner, 2.05. And by standard estimates, the 95% confidence interval is 1.86 to 2.23. So this number does not differ significantly from 2. Neither does this slope differ from 2. Neither does this slope differ from 2. In fact, none of these slopes differ from 2. They're all approximately 2. So there are two empirical findings here. One is that there's a linear relationship of variance to mean on log-log coordinates. And the second is that the slope of that on log-log coordinates is approximately 2. Now, if cases were Poisson distributed, that is randomly distributed, the mean and the variance would be equal. That's this theoretical reddish line here. This is what happens if you have a Poisson model. It's clear that there is more clustering by county than random, because these lines are nowhere near together. Okay, that is for cases. Cases. Are there any questions about that? Here's the same slide for deaths. Again, everything is the same except the count is now deaths. You see the data starting down here and moving upward to the right. And again, the only case, well, here, the only case that where the confidence interval does not include 2 is April 2020. After that, the confidence interval includes 2 everywhere. And it gets close to 2, 2.0000, 2.001, 2.0019, 2.0167. So it's very close to 2. The major findings are counties' cumulative counts of cases or deaths. The slope is close to 2, and the log variance increases state by state linearly as a function of the log mean. Now, why? That's the question I want to address. So here is an idealized data structure. It looks like the previous slide. We treat each state as if it were a sample. And we put the sample headings, the state names across the column headings. And we put the county counts of cases or deaths down the rows, and we calculate the mean and the average. This structure is known in ecology since at least 1941. That is 80 years ago. And it was popularized in 1961 in a paper in Nature by this man, Lionel Roy Taylor, an entomologist. And the columns corresponded to samples, and the elements corresponded to counts of insects. And Taylor's law says that the variance is approximately some power b of the mean, or the log variance is a constant log times a plus b times the log mean. And what we found is that b is roughly 2 most of the time here. If you divide both sides of this equation by the mean to the power b, it says the variance divided by the mean to power b is roughly a constant, or constant distribution. Taylor measured population density. The pattern applies much more widely. That's Taylor's law, a power law relationship of the variance to the mean. Taylor assumed that the variance and the mean are finite. But there is a whole world in which of distributions that have infinite mean and infinite variance. And when I learned that, wonder, fear, and astonishment. The sample mean and the sample variance are always finite. But if the mean or variance are infinite, then the sample mean or sample variance, they don't converge to a finite value, but move toward infinity with increasing sample size. So we need a different kind of mathematical theory. And the beautiful talk by Gennady Samorodnitsky on the first day of this conference showed some of the results that he and Richard Davis have proved about Taylor's law when you have infinite mean and or infinite variance. This is a continuation of joint work with Gennady Samorodnitsky and Richard Davis. You can diagnose whether a probability distribution has an infinite mean or variance by looking at its upper tail of the survival curve. So the survival curve is the probability that the random variable x is greater than little x as a function of the little x. And if on log coordinates, the probability of survival beyond little x goes down with slope -1 or less, with less than -1, then you have infinite mean and infinite variance. If you are in this region between slope -1 and slope -2, you have finite mean, infinite variance. And here's where all the distributions that Taylor thought about live, with finite mean and finite variance. But there's these whole worlds over here that Taylor didn't think about. Here are the COVID-19 data. The survival curve, the vertical axis on log coordinates is the probability that the number of cases is greater than or equal to x, and the horizontal axis on log coordinates is x. So the probability drops off that the number of cases in one county is bigger than 100, 1,000, 10,000, 100,000. And it looks like that. It's not a straight line, so we know it's not a Pareto distribution, but anyway, this is what it looks like. It's a shouldered distribution and comes down. It looks like it might even be straight down here. We'll examine that further. This is the same thing for deaths. And again, it comes down with a curvature. So to summarize, the cases and deaths by county are not Pareto distributed. If they were Pareto distributed, those would be straight lines. Now we zoom in to the counties with the highest 1% of the number of cases or deaths. So this is just the biggest 1%. And the relationship is approximately linear for all of the 15 months that I examined up to June 1st, 2021. And I estimated the slope and the 95% confidence interval of the slope. And you see that the confidence interval includes -1 here, but not after that. After that, it's between -1 and -2. Here, 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 here. All of these confidence intervals for the rest of the pandemic are between -1 and -2. That says that the distribution has finite mean and infinite variance. That's for cases. What about deaths? Same story, except that it takes until August 2020 to exclude -1. Here the confidence interval includes -1, so it could have infinite mean too. But after this, it has infinite variance and finite mean all the way after that. To summarize, the highest 1% of counties' cumulative counts of deaths or cases after the first few months, the survival curve on log scale decreases linearly as a function of log x, and the slope is between -1 and -2. The empirical survival curve suggests the variance is infinite. So what? If the variances of cases and deaths per county are infinite, facility and resource planning should prepare for unboundedly high counts. No single county, state, or other jurisdiction can prepare for unboundedly high counts. Cooperative exchanges of support should be planned cooperatively in advance. The same way we share firefighters across states, we need to share preventive and curative resources. So we need a theory to explain what has been shown here. A theory of Taylor's law for multiple samples of heavy-tailed data. How do the sample mean and sample variance behave in multiple samples with fixed or similar sample size when the data come from distributions with infinite variance or infinite mean, and there are roughly as many samples as each sample size? So here's a simulation of an idealization. I need to tell you what is a probability distribution with regularly varying tail, upper tail, survival curve. And if you understood Gennady Samorodnitsky's talk, you already know this. So X is regularly varying with index alpha if for every fixed t, the limit as x goes to infinity of going out x times that compared with the probability of survival beyond x or having more cases than some quantity x is 1 over t to the alpha. And what that means basically is that the upper tail is a slowly varying function. The upper tail is a slowly varying function divided by a positive power of the cutoff point. A slowly varying function satisfies this. This is a repeat of what was in Gennady Samorodnitsky's paper. And if x is regularly varying with index alpha, and alpha is between 0 and 1, then all moments greater than alpha are infinite. If alpha is between 1 and 2, the mean is finite, but the variance and all moments higher than alpha are infinite. If alpha is greater than or equal to 2, it has finite mean and variance. All moments up to alpha are finite. Beyond alpha, they're infinite. So we created square matrices. We simulate, now we're going to do a simulation. Square matrices with 10 up to 1,000,000 rows and columns. And we fill them with IID elements. Regular, is there a question? Okay, regularly varying. And we plot the log variance of each column as a function of the log mean. And what we find is that for larger means of large samples, slopes are close to 2, which is just what we found in the data. For example, we can simulate the Levy law, which is a stable law with tail index 1/2, by taking the absolute value of a standard normal random variate. Any computer will produce that. And we square it, and then we take the reciprocal. So it's 1 over a standard normal squared. And if we fit a straight line when we have 1,000 or 10,000, we get a slope. You can't see, it says B 1.9998, and this says B 1.9997, very close to 2. That's what we saw in the data also. And the coefficient A is very close to the sample size or the number of samples. So it's 1,000 here, it's 1,003. 10,000 here, it's 10,056. Very close relatively. So we took the case where the rows and columns are 10,000, and we considered alpha, the tail index, 0.11, 0.22, 0.33, 0.44, 0.55, 0.66, 0.77, 0.88. In all cases, the slope is very close to 2. This shows for plots alpha, and the highest one, the greatest deviation is 2.004. So the slope is very close to 2. What happens when alpha is between 1 and 2? Well, for samples of size 1,000, the slope is not super close to 2. It's 2.23, 2.2658, 4.24. If we increase the sample size to 10,000, the slopes get closer to 2. And they get still closer for the next, for 100,000 samples. And they get even closer for 1,000,000 samples. This computation for this slide cost 53 hours on my computer. So here's the estimated slope for samples of size 1,000 up to 1,000,000 for values of alpha between 1.25 and 1.75 for the 5 largest values. And except for this fluctuation here, the tendency is closer to 2. So those are what the simulations lead us to expect. And I thank Richard Davis and Gennady Samorodnitsky for taking these conjectures and turning them into mathematical proofs. They proved, and I'll show you more precise statements, that the upper tail of multiple samples obeys Taylor's law with slope 2. And I am very honored and grateful to be collaborating with them. So here is one of their theorems. Taylor's law holds when alpha is between 0 and 1 with high probability. WHP means with high probability. The logarithm of the variance is the logarithm of the sample size, number of rows in the matrix, plus coefficient of slope 2 times the log of the sample mean. Now, where does this come from? If you look in this formula at the bottom of the slide, if you take the logarithm of the variance over this squared, then you get the log of the variance, that's this, minus the log of the denominator. Well, the log of that is log R, and the 2 comes down and you take the log of the mean. And this statement says the probability that the absolute value of this quantity is bigger than any epsilon, no matter how small, approaches for any j, satisfying some other condition, approaches 0 as the sample size goes to infinity. So that means high probability this holds. Now, what are the conditions? They are complicated, and for the purposes of this talk, I'm not going to go into them. But basically, they include the kinds of samples that I showed you in the simulations. This result says they have equal distribution and that they are conditionally independent. So the assumptions in my simulations that they are IID and that the different columns are mutually independent can be relaxed, and the same law holds. You can start off with Zij as an independent, identically distributed space-time process with regularly varying distribution with index alpha in 0 to 1. And then you take a Gaussian process with arbitrary covariance function. And the product of these two, they're conditionally independent, but not identically distributed. So the marginal distributions are different. Under the assumptions in the previous theorem, the conclusions hold. What about when alpha is between 0 and 2? Same conclusion. With high probability, you get this linear relationship. That's Taylor's law with slope 2. And here we are, for simplicity at this time, assuming IID elements. So there's more to do. We'd like to relax the assumptions of this theorem, but at least this is a proof that covers the simulations I showed you. There are 2 relevant prior papers. The first paper to show that Taylor's law works for any distributions with infinite mean was by Brown and Victor de la Peña and myself in the Journal of Applied Probability in 2017. And the results that Gennady presented beautifully on Wednesday are in Proceedings of the Royal Society 2020, December. And this is one part of a beautiful walk that I took in France in 2019. I'm sorry I can't join you in Paris, but this is a baffling set of stones that I encountered. And thank you very much for the privilege of talking with you. I welcome any questions. And you have my email address on this slide, so feel free to write to me. Thank you.
So thank you very much, Joel. It was a really good talk. It was really a very good good complement with together with the talk of Gennady. It was really very great. Okay, so are there any questions maybe or comments in the public or somewhere else online? No?
I'd like to thank you, Paul, for organizing this conference and for allowing us to join you. I know this is a tremendous amount of work, and you are very good to bring us all together. So I really salute you with many thanks for your leadership.
Thank you very much. You are very kind, and I hope we finally have a real conference all together. It will be great.
I agree. I pray for the same.
Okay, we will welcome you in Paris whenever you want. Okay.
Thank you.
And I want to thank you again because so Thank you very much for the talk. Thank you very much for all the afternoon's talk. And also I wish to thank all the speakers in this conference, which was really of a very, very good and very nice level, and all the talks were very nice. So I am extremely thankful to all the speakers. So I hope simply that very soon we can have the real things. Okay. So I cannot offer you a drink right now. That's a pity, but I hope it will be very soon possible. Okay, so I just close the conference. Thank you to all the people who attended online, and okay. I wish there will be many. Also, I should say, I see that there is still Donatas online, and I really hope that we can go on with those stories of long heavy tails models, and maybe even in the case of different data sets. So that's our plan with Gennady and the Donatas at least. Okay, so thank you very much, and I just stop the recording, and I wish you all the best, and have a good day and have a good weekend. Bye-bye.
Bye bye.
Bye.